for about an hour. You will do the question answers and will get replies. Then I will try to finish the micro electromechanical sensors session lecture which I started yesterday. In the second half, we will go back to lab, okay, and we'll try to finish the pixel design which we started some time ago. Tomorrow we'll keep the whole day for lectures again. We will see if we get time. Maybe we'll do a bit of MATLAB exercises on micro electromechanical sensors. Okay. Then Thursday, Friday will be a mix of lecture and tutorials. Saturday onwards, the local host, Professor Muralidhar and Professor Srihari Rao sir, will take over. Okay. So by Friday evening, we would like to finish everything which I have to teach you. And if you have any doubts, you can ask me at that time. Okay. With that, so you all have, I've given you the web page link which also contains a soft copy of these slides as well as the soft copy of the book which we are going to give you, but you are going to get a physical copy anyway. Now I have been told I can conduct an examination. Should we do an exam? Keep it off with the afternoon, maybe I'll need it. Good. So let's do some set of question answer sessions. Okay. Just give me a wee sec. So these are typical questions which I make my students go through. So question number 1, which talks about a 600 nanometer form. So what is 600 nanometer? Which color? It's in between. It's the green color. Right. Now question 1, most of it you should be able to do. We did a similar problem the other day, didn't we, wherein we calculated the energy of a photon, a red photon and a blue photon. So it should be in the same ballpark. Next is the second question. Now all of you have done some digital electronics as part of your undergraduate. So let's take this question. We have an array of 3 transistor pixels. What we now need to do is we need to read each row. So I keep on saying we have row select in a pixel, and we would like to read each pixel one at a time. We have to design a digital circuitry which does this job. So we read the pixel, we read its value output, then we reset the pixel, and then we move to the next row. Read the row, give a certain time to read it, and then reset it. So how will we go about designing this digital circuit? What kind of circuit will it be? Either we design it or we have a discussion. Okay, so go on, tell me what kind of circuit allows me to give one output line, and after a clock pulse another output line, after another clock pulse another output line, after another clock pulse another output line. Because I have 1000 rows to read. I can't read all the rows at one go. I'll be reading first row. And then I have to disable the first row and enable the second row. So how will I go about designing a digital circuit for that? A mux. Okay, somebody says a multiplexer. Now multiplexer would have been a very good circuit had we wanted to randomly read any particular line we want. Okay, then we could say, okay, go and read line number 340, and I will give my 340 as the address, and then it will select that particular line, very much like what we do in memory. We have memory address decoders which get an address and they select. But here we are not interested in doing that. We are not interested in reading a particular line. We are interested in reading all of them. And we are interested in reading sequentially, first row, second row, third row, and so on and so forth. So what would you then advise us to go for? Matrix, what kind of digital circuit is that? So what am I doing? So say I am giving a start signal at the beginning. What I am doing to the start signal, it will be a clock pulse, right? I am essentially shifting it from one row to the second row to the third row to the fourth row. Agreed? So which circuit can help me do a shifting operation? Shift register. So it will be a fairly simple shift register. How do we design a shift register? With D flip-flops. So sequence of D flip-flops, one after another after another. Okay? So keep this in mind. I will ask you to design this in the lab. So we'll give you a D flip-flop. I don't want you to, okay, if you are interested, you can go and build a D flip-flop as well. But most probably I will design a D flip-flop myself and give it to you. But there are two parts of the question here. So if there was a single signal which just I am shifting, a D flip-flop would do the job. But now I have to do this. When I am reading a row, I am resetting the previous row. So how will I go about doing that? Yes, an AND gate will do. I can have a reset line. Alternatively, if I am very mean, I can use the source row select of the next row to become the reset of the previous row. So while I am selecting the next row, I will reset the first row. That would also kind of do the job. Okay. Question 3 is again a bookwork exercise. KT oversee, a number of you would have done in your school work sessions. So we'll kind of bypass that, but I would like you to do question number 4. So we derived the output voltage of a linear active pixel sensor the other day. Now I am asking you to derive the output voltage of a log pixel. So this is a logarithmic pixel which we saw yesterday. What I want you to, I have given you the formula of the current flowing through M1. That is the formula. From there, give me what will be the output voltage. And I once again assume there is a current source feeding the source follower. So there is a I bias current source which is moving through M2 as a source follower. Would somebody like to come and do it on the board? Or would you guys like me to do it? There is a yes to both of them, and I cannot figure out. It's an either or question. You cannot have yes to both, right? BJP, yes. Congress, yes. And what's the local party in Telangana? Is the, what's it called now? It's called TRS, BRS, or maybe ARS someday, Asia Rashtra Samiti. I'm going by the way it's progressing. So, yes to all the three parties. Huh? What would you like? Would you like to give it a go and give me the solution? Ever ask a student, would you like to do some work? The answer is always no. Morning, sir. I'm still only having smiles from your side. I want the solution, not the smiles. We're electronics engineers. We don't have much use of smile in our field, do they? So I did part of it yesterday. So go maybe think on these lines. Where is this? So this, the drain current of M1, where is it coming from? It cannot come from the gate. It cannot come from VDD. Well, it can come from VDD. That will be the drain current. The drain to source current. The only source for current is either VDD or the photodiode. Where is photodiode getting its current from? Light. Light is falling on it, it's producing a current. Now, what are the currents produced in a diode? One is the photocurrent, the other is the diode is operating at room temperature. So, what other current do we get in a diode? Is thermally generated reverse bias current. There will always be a thermal current because heat by itself produces some electron hole pairs. We are at room temperature, that will produce some electrons, so we will get some leakage current. So, we will have so the total current produced in the photodiode will be the photocurrent plus the thermal leakage current. Where does that current go? It cannot go here. There is a gate. The only place it can go would be M1. Now, we also know from the calculation which we did in the day 1 that typical photocurrents of this size diode are of the order of femtoampere or picoampere. They are quite tiny current. So, they are not big enough current to put this transistor into any saturation. So, transistor plus on top of it the gate, the VGS and VDS of the transistor are exactly the same. So, transistor is getting on, but not going in full saturation region. So, it is going in its subthreshold region. I have already given you the expression for subthreshold region of operation, okay, where these terms are there. So, if I rearrange that equation, so what is the gate voltage here of this M1? What is the gate voltage applied to M1? VDD. What is the source voltage of M1? That is kind of the input of M2 as well as the node of photocurrent, right. So, if we call it just Vs for the time being, so now I have got VDD minus Vs here, ID becomes I photo plus I dark, okay. Then I can rearrange this equation. What will I get when I rearrange this equation? I want this in terms of Vs. Oh, sorry. What kind of relationship will I get at the voltage at this point and the current flowing in diode? So, relationship between current and voltage is exponential. So, the relationship between voltage and current will be logarithmic. So, I am getting a log voltage, okay. So, that part is clear. So, once I know this voltage, how is this voltage related to this voltage? What kind of amplifier is this? So, think of it this way, in most MOSFET amplifiers fairly easy. Where is the input? On the gate. Where are we taking the output? This is drain. Drain is connected to VDD. The output is at source. So, terminal left is drain. It is a common drain circuit. Okay. Common drain is also called as source follower. So, it will have a gain of kind of 1. But we know from theory we do not get actual gain of 1. So, one of the exercises which you should do today when we go to Cadence lab is find the gain of a source follower circuit. So, design a source follower circuit with the smallest size transistor and see how much gain you get. What do you expect to achieve? It will always be less than 1. You would be lucky if you are around 0.78, 0.8 kind of gain. Okay. Now, tell me what kind of fixed pattern noise will this circuit have? What are the sources of fixed pattern noise for this circuit? Again, we will be using the smallest size transistor everywhere. Right? Now, some of you started simulating the 3 transistor active pixel sensor. changing the active pixel sensor to this circuit is not very difficult. All you have to do is to convert the gate of the device straight to VDD rather than a pulse. So let's try to simulate this circuit today as well. Okay, this is much easier simulation than an active pixel. It's not a transient. It will be a DC simulation where all you will be doing is changing the photocurrent applied to your diode. So what is the relationship I expect to see here compared to this photocurrent? Now I was going to do this as part of a lecture, but I will do this here as tutorial. So if you can see me on the board. So what we agreed that our I drain, IDS is I photo plus I dark. Agreed? Or I leakage. And the computer Baba has decided not to show you anything. Okay, it will come in due course of time. And then we decided, oopsie, you see that? Okay. And now we are saying that this is also equal to some I naught, some constant, times e to the power q times VGS minus VT. And now which transistor VT we should be looking at? Transistor 1 divided by KB times T. If I rearrange the whole equation, what I should get, my Vs is equal to VDD minus VT1, would be minus KBT times Q natural log of I photo plus I dark. Okay? Now let's look at the source follower circuit. If I have a simple source follower and I provide a current bias here of IB, so I already know this equation. Vs, this is just a switch, so I'm kind of going to assume it's an ideal switch for the time being. All I need to know is what's this voltage going to be. So once again, what we did on Sunday, we assumed this transistor to be in active region of operation. I'm going to provide a high enough current. Remember, this current was of the order of a microampere. It was fairly high compared to the photodiode. So drain to source saturation region equation for transistor number M2 will be beta by 2 VGS minus VT square. That gate voltage is this Vs of 1. Okay. Now we are talking about VGS2. Okay. And the source voltage here is kind of my output voltage now. Hence, my V output is going to be from here VG2 minus VT2 minus square root of 2 IDS2 divided by beta 2. Agreed? Overall, if I place this equation here, I will get a longer equation which will have threshold 1 and 2 and beta 2 together. So this your VG2 is all the same as VS1. Now let's look at where are we going to get noise in this, the fixed pattern noise, where is it going to come from? We said the threshold voltage of two transistors is not going to be alike when you are making them very small. Now I have two transistors here, VT1 and VT2. So that, okay. So both threshold voltages are not going to be the same. But the beauty is both of them are appearing as additive terms. They're adding something to my signal. There's beta 2 which is not going to be same either. But if the change in beta is small, I can linearly expand it as a Taylor series as an additive term as well. So as a sum total, if I have to write it as a parametric equation, I can write this as A plus B natural log of I photo plus some C, whereas A is all of my additive terms added together, B is this term here, kBt by q, and C is the dark current. So essentially we can model this pixel, this fairly initially complex pixel with all these equations as a very simple 3-parameter equation. The reason I'm bringing this 3-parameter equation to you guys now is to ask the question, I know all of these parameters are going to be different from each pixel. Even if I show a plain white image to my pixel, each parameter is going to be different. So how do I correct for noise here? And I'm not even looking at temporal noise. Let's just look at fixed pattern noise for the time being. So if you are given a sensor and you have been given a million sensor where the input is the same, but you have these numbers are different for each pixel, how will you go about correcting this sensor? So what are the errors I need? So say I have two pixels. Pixel 1, which will have its own A1 plus B1 plus natural log of I photo plus C1. Pixel 2 will have its own A2 plus its own B2 plus its own I photo plus C1. At this point, we know we are exciting both pixels with same light. So ideally, the thing which is common is I photo, and that's the one which I need to know. Right? So essentially, I need to know how much light is falling on it. But because of these different A1 and B1, I'm getting a different voltage as my output. So how do I calibrate this pixel array, to get my photo current? We will see exact circuits on how to do that in the afternoon session. But for the time being, think of it this way. My A1 is untrustworthy. I don't know what its A1 is. Whether it is, so I would ideally like to remove it from my equation. So how can I remove A1 from this equation? For the time being, to make your life easy, let's assume this is too low. So I'm just going to model it as a much simpler A1 plus B1 log of I photo. How do I remove A1 from this circuit, from these equations? We told you a trick yesterday. Take the response at 0 input. So if my I photo is 0, what's my V output? So let's call this V1, and the same pixel V2. At 0 I photo, I will just get A1 as an output. If I take the difference of these two, so V pixel response minus V pixel dark, all I will get is a B1 log of IPH. Agreed? That will be an easy way to remove my offset related. So this is the offset error which we have got. How do you remove the gain error? Because B1 is also different from pixel to pixel. So how do I normalize this B1? Come up with a technique. So this is the multiplicative error. So I cannot take another signal and just subtract it. So how do you remove a multiplicative error? What's the mathematical operation which gets rid of multiplication? Division. How do I divide? What do I divide it with? So I could argue that, okay, my first one went out by 0 input. What if I give a known input to the signal? I know my photocurrent, a calibrated input. Then my V pixel third output will be the same A1 plus B1 plus I photo known. Okay? So if I know I'm exciting it with X amount of light, I can do the subtraction from dark for both of these and get rid of my A1. Right? So VP3 minus V pixel dark will just be this area. Now I have these two. I can always do V pixel 1 minus V pixel dark divided by V pixel 3 minus V pixel dark. And if I take the ratio, B1 disappears. All I would be left with log of I photo divided by log of I photo known. Okay? Sorry? If C1 is also changing? Yes, yes, yes. We are coming. Now, ideally, this should have been I photo plus C1 here, and I photo plus C1, I known plus C1. Okay? So, C1 does depend from pixel to pixel. Okay. At this point of time, we have assumed it doesn't, so that I can do a simple linear mathematics. Okay. So, before I come to C1, there is another question which we need to see. Now, I am saying in order for my camera to work, I need to take one picture of the live scene, one picture of the dark scene, shutter close, and one picture by exciting my pixel with a known light. So, remove the scene, excite it with a known brightness. It's tricky, isn't it? Unless you have got very controlled scientific environment, it's very difficult to do that thing. So, how do we go about designing a circuit which will do this job? Now, we need to do it electrically, this operation. So, dark scene is comparatively easy to build. You just disconnect the pixel from rest of the circuit. Okay? So, let us try to see how it will happen. So, we started as a tutorial and I am ending up doing a lecture again, right? Okay, no worries. So, when I said we excite with another voltage and another photo, another light, what essentially happens in the pixel? Essentially, I get a different photocurrent. Agreed? Now, for the rest of the pixel, it doesn't matter where is this current is coming from. Is it coming from light or is it coming from an electrical circuit? It doesn't matter, right? It's always going through the same operation. So, what if we have an electrical circuit which produces a known current? Now, electrical circuit, I can control that. I can feed the same current in many pixels at the same time. How do I do that? I can build a current mirror. Essentially, what we could do is we could have the same pixel circuit so rest of it is same. What I want to do, I want to have three instances. At one instance, this current flow through this transistor. At another instance, my known photocurrent flows through this transistor, and that could be a high current. Right? So, I could have a current source in parallel, or I could just put a transistor. I could just apply a known voltage on this transistor. It's a transistor gate to source is sorted to ground. I apply a voltage, I will get a current in drain, okay, by the same relationship. I can have this by a switch to this node, and that could be my calibration switch. So what I could do is, fine, light is falling on this. I put another current in parallel, but make this volt current too high compared to the light. So I don't need to disconnect my diode. If it's too high compared to diode, it will overimpose this on this anyway. But rest of it, so say I know my current is of the order of till a nanoampere. I feed a microampere here. Rest of it loop remains the same. So I could have a calibration switch, which in turn helps me calibrate the whole of the circuit. To switch this thing off, we could also have a switch here, which basically disconnects the diode from the pixel. Okay? Now this is where theory works brilliantly. Disconnecting the diode from the rest of the pixel is not easy, because see, we are having all of these are NMOS type transistors. So ideally we would not like to bring a PMOS type transistor in the pixel, because PMOS means more area. So we are constrained with the area here. NMOSs are not very good closed switches. So what happens as a result, there is always a leakage which flows through this. And this is why disconnecting the diode, we tried it as part of my early PhD and realized it much later that we couldn't disconnect the diode. The only way to disconnect this was to put a very high negative voltage on this. I mean, by very high I mean minus 0.5 volt. And for a circuit which only operates between 0 and 3.3, minus 0.5 volt is a fairly high negative voltage. So what we could do here, but a simple calibration switch in parallel helps us get those 3 parameters. The question then you should ask is, why do this at every frame? Come to think of it, are my A, B, and C's changing? Once designed the pixel, it remains kind of constant. The only thing which was changing was B, which in my case was nKT by Q, where T is temperature. So that's temperature dependent. Fortunately for me, my end customer does not change his temperature frequently. I don't have an end customer who takes picture in the morning at minus 5 degrees Celsius, in the afternoon goes at 50 degrees Celsius. It happens, but not frequently. Okay? So I can kind of assume these to be fairly constant with time. So one thing which we could do is, rather than doing this operation every time I'm taking a picture, do it once, find A, B, and C of each pixel and store it in a frame memory. And every time I get the pixel output, do the reverse operation. Reverse operation here would be, so I saw my V output is A plus B log I photo plus C. The reverse operation would be I photo is equal to V output minus A. So if I have A, B, and C, I can do this inverse operation. If only life was that easy. So why do you think I would not like to do this? I can do it. We have done it in past, but there's a problem doing this. We can do exponentiation. That's just inverse of log. So there are op-amp based circuit which you can design to make an exponent circuit. So what are you doing when you are doing log of a signal? You have got a big signal, you're compressing it to a small signal. Okay? What you're doing when you're doing exponent of a signal? It has flown in. I will take something else. You have got a small signal, you're expanding it to be a big signal. But the small signal was recorded under certain noisy condition. Like you are saying, these two levels I can find, in between there is some noise here. When I'm expanding, all these gaps in expansion are also being filled by that noise. So, say I said I knew 1 volt accurately and 1.001 volt accurately, and this is now becoming 1 volt and 3 volt or 3.003 volt. I am multiplying it by 3. Let us take a very simple example. Then all the gap here is being filled with unknown noisy data. So, doing logarithm is a very good operation. It compresses the signal. Doing the inverse adds extra noise to the system. Okay? So, doable, but not advisable. Somebody asked a very good question. What about C? That's not a very nice operator. None of this mathematical operator. I did very simple maths to find A and B. How do I find C? I could take a third mathematical operator. What I could say is, after I have done my subtraction, after I have removed my A, I have got B log I photo plus C, and the dark response is B log C. Okay. Now, I don't really need to know, I mean, if I subtract these two, what will I get? I will get B log I photo plus C divided by C, am I correct? So, I will get I photo as a function of C. Now, you can do mathematical operators to find out. One of my senior, Dilip Joseph, did something even more interesting. He just estimated it by iterative operation of 24 different images. So, you have, rather than just taking 2 white lights, you have different light ratios. So, you have got V1 out as a response of I photo 1, V2 as a response of I photo 2, V3 as I photo, and you have tons of these, and you do a reverse estimation to find these ABC out. Okay. So, that way I can calibrate for all of these. So, this is another trick which we often use with another type of sensors, is when we have systematic errors in the system. So, one are the random errors happening because of noise and everything. The others are systematic error. I know there is there's a functional relationship between my output and input. My input goes through some mathematical operation here. I can find the parameters of those mathematical operations, do a reverse operation to remove the effect of these mathematical operations. Calibration comes with a cost. And the cost being, if you have a large array of system, you need a large memory to store all the calibration parameters. And as the pixel data is coming, you need to recalibrate each one of them. So, larger pixel arrays are difficult to calibrate because you need a faster processing system to do that. Okay? Good. Let's now go back and see where we were in. Wake up, wake up. Now, I am showing you a different circuit. We will see why this circuit came up. So, I really like this circuit because it gave me the best paper award in Midwest Symposium. This is not the circuit we designed. This is the circuit which we ended up getting by fluke. Now, this is also a logarithmic, kind of a logarithmic pixel, but I have also added a reset signal to it. Now, I need to tell me what kind of response will this pixel give me. And think for a little bit. So, if you remove that reset transistor, this pixel looks like the logarithmic pixel which we are just working on till now. If you remove the log transistor, this pixel looks like the active pixel sensor which we have been working for last 3 days. I have merged both of them. how will the response look like? And to start with, let's assume my VDD is bigger than V bias. This is actually a very interesting circuit, not from its application point of view, but from an, so think of this way. So I said my VDD is bigger than V bias, okay? I apply a reset signal first. What happens to this node? I get that some VDD minus VT coming here, or if there is a very good switch, I almost get VDD at this point. Agreed? VDD is bigger than V bias. So what happens to this transistor? The source voltage is bigger than its gate voltage. Okay? If in a MOSFET transistor, if its source voltage is bigger than gate, which region of operation is the transistor working in? The source voltage is bigger than the gate voltage. So what's the gate to source voltage? Maybe I will have to, you guys don't like me sitting down, do you? So what we are now saying is the source voltage of transistor M1 is bigger than the gate voltage of transistor M1. So VGS of M1, that's going to be negative. Am I correct? Gate minus source is going to be negative. If the gate source voltage of a transistor is negative, which region of operation is it working in? Cut off. Well done. That's switched off. It's not part of the circuit. Okay? So let's start by doing this thing. So I apply a reset voltage and leave it. That's my reset signal. Now my photodiode is still producing current. Light is falling on it, it produces a current. So let's look at that node. Let's call that node again N1, okay? So node N1 goes up high to some VDD minus some voltage, but VDD to start with. Transistor M1 is switched off. So right now, my circuit is acting like a normal active pixel sensor. What happens in a normal active pixel sensor? What happens to this voltage? It starts slowly falling down. So it starts falling down. Now, as it starts falling down, at some point, it will become lower than that V bias. Oh, come on, stop switching off. So at some point, my node 1 voltage will become lower than V bias. So this condition will become exactly the opposite. My transistor will start switching on. Great. And as it starts switching on, what happens to that current? That current starts flowing through the transistor. And when it starts flowing through this transistor, it starts becoming, what kind of relationship I get between current and voltage? The logarithmic relationship. We just saw the logarithmic relationship. To start with, it's a linear pixel. But after a while, it becomes a logarithmic pixel. So if you plot the response, say photocurrent versus output voltage. So for the smaller photocurrent, it acts as a linear response. For higher photocurrent, it acts as a logarithmic response. So now this is a task for you guys. How will it look like if I have got this in the log scale? The logarithmic response will look something like this, right? On the bottom, I have got log 1, 10, 100. So logarithmic response will look like a straight line. How does a linear response look like? That will be a lab assignment for you. Go and figure it out. It becomes a curvy, like it looks like a parrot in the end. But the pixel is very interesting. Now, the reason why it's interesting, so where do we see the most amount of information? Is it in bright light or is it in low amount of light as human beings? Okay. Where is more signal available? Or where do we want more signal to be available? In the low light. Because when we are integrating, remember when we have integrated, in the low light we have less signal. In the bright light we have a good amount of signal. So in low light, if we do logarithmic compression, I get even less signal. So from a good pixel point of view, in the low light, I should expect a linear response. A linear response will be better for me. So the pixel gives me a linear response in low light, but a logarithmic response in high light, which is kind of good. It ticks both the boxes. Can somebody tell me problems with this design? So one problem, of course, is I'm still making my transistors from the smallest size possible, which means I will have fixed pattern noise. I will have mismatch. Now I'm adding a new type of mismatch. My pixel moves from linear to logarithmic. The point at which it moves from linear to logarithmic will also vary from pixel to pixel. Okay. There's a slightly bigger problem here. And the problem is not just from these pixels. The problem is also from the human visual system. At the beginning, I said we do some form of logarithmic compression in our human eye. It's Stevens power law compression. At the same time, yesterday we talked about color. And we said color we get by red plus blue plus green. How do we get color when we have got log of red, log of blue, and log of green? We get color by linearly mixing individual colors. If my individual signal is the logarithmic of that, how do we produce color? Do we do anti-log, then add and then do log again to get color? Doing anti-log, as we discussed, is a noisy operation, which then leads to the question, how does the brain do it? We know human eye does logarithmic compression of input signal. So how do we see color from that log signal? When you find the answer to that question, send an email to the Nobel Prize Committee. It's still poorly understood at best. You can essentially do log R plus log B plus log green for small signals, because for small signals, log of x is equivalent to x. But for bright signal, the same relationship does not always remain true. Okay, let's do one more question from our pixel diagram. The other pixel which I discussed the other day was this pixel. So this was another patented pixel of ours, which basically has a comparator inside each pixel. Remember we talked about this idea wherein why don't we feed a reference signal to the pixel and put that comparison as a metric of the signal input. Now comparators can be very large. So I designed a comparator saying, why can't we use a single transistor as a comparator? Not a great comparator, it's not a brilliant comparator, but it kind of works. Think of it this way. If this voltage is low to start with, and this voltage is high too, so this is the voltage which is there due to pixel being reset. Okay? So gate voltage is high, this voltage is low, this transistor is on. Right? So whatever appears here will kind of appear here as well. It's an on transistor. Good. So at this voltage is now falling down and this voltage is going up. So, at some point of time my VGS will become negative. This transistor will switch off. At that point of time, whatever is held here is held on these capacitors. There is no place for that charge to go away. While this voltage keeps on going down, this transistor is off. Whatever was here is being held on this capacitive node. Now, your task would be to find a relationship between these output voltage and the input photocurrent. How will we go about doing this? At this point, you guys are saying, you are asking the question, you are solving them, why don't you solve this one as well? So, I will give you a hint, but I really expect some of you to try this on. So, this signal is going down. What is the relationship here? We can map it as a linear function, right? A minus B of photo current. This signal is going up, which is another similar relationship. So, how do you find the point at which they interact? So, how do you find when there are two waveforms which are going up, how do you find the point at which they will cross one another? So, let us give you two functions, a1 plus bx and a2 minus bx or bt. Okay. Now, let me tell you precisely the problem here. Oh, for heaven's sake. The function which is falling down is sum a minus b times I photo times t, okay, or you could have said I photo times c PD. Okay. So, there is photocurrent and time there. The other function which is going up, my reference function, this is my V node Ni, my reference function is going to be sum A ref plus B ref times time. There is only time here, it is just going up with time, there is no photocurrent here. At some point they cross. That crossing point I will get a certain voltage. I need to know that voltage as a function of I photo. There should be no time involved anymore, because once they have crossed at the same time. Okay. So, my output function, which I am keeping it same, so once they cross I keep it same, that should become a function of my photocurrent. That is what I want you guys to find out. And then we will make it more complex to see, can I get a logarithmic response out of it. Tell me, how would you go about doing it? Even if you don't want to do it right now, tell me, how would you go about doing it? Is the question clear? For those of you who are still thinking, think what happens at the time they cross. What is common between these two signals? Time. Well done. So, we write these two equations in form of the time and equate those two. Done. Okay. So, can somebody give me a quick relationship between V out and I photo? for this one I am going to wait. So this is a comparatively easier problem. Well, we'll come to the harder problem in a minute. Yes. Okay, the more longer we wait, the longer the coffee break will get, right? Ah, sorry. I can give you the solution which I just showed you on the screen. But ideally the problem should be fairly straightforward. If you find time from the first function, which will be Vni minus Ai minus Vni multiplied by C divided by I photo. If you find the time from the second function, which is Vref minus Ar divided by Br, equate the two timings, you will get a response function which will have Vref as well as your V output. Okay? Or you will get a time at which these two will be common, and then you put the time back in this equation, you will get a V output equation. Now that's a comparatively simpler problem. The harder problem is, I said I can get any monolithically increasing function from this one. If my customer then comes and says, you know what, I don't want a linear, you can see this will be a linear response, two linear functions meeting one another, I will get a linear output. I want a logarithmic output. So I know what kind of output I want. How do I go back and derive the reference function which is needed? That actually cannot be derived. There is no mathematical closed form solution to that problem. Actually, I can show it to you how it looks like. Oh, what are you doing? What you end up getting is a formula not between the reference function as a function of time, but what you end up getting time as a function of the reference value. So what I would have liked is how does my Vref changes with time, but inverting this function is quite challenging. As you can see, we have Vref here and we have Vref also in 10 to the power, or right? So inverting that function becomes very challenging. But that's not a problem, because essentially what you are saying is V is a function of time. I don't know that, but I know time as a function of voltage. I can still plot that value. Okay? Good. This problem again we did last time when we tried doing a speed of ADC required for a camera. When you make smaller cameras, we don't try to have one ADC per column, particularly when you're making things like cameras for endoscopes, wherein you know you're not going to get very high pixels, so the camera has to be very small, as small as possible. Right, we have been talking for about an hour. I said I will give you a break after an hour, so let's take a break of 10-15 minutes, and then we'll come back to continue our microelectromechanical systems work. And we'll go to lab in the afternoon. Tomorrow we'll revisit camera pixels and we'll do a bit more advanced pixels. Till now we are only going through the simpler pixels. We'll go in more advanced designs of these. Okay? Having said that, whatever you have learned till now, that actually is enough to make a camera in industry, and most of the pixels which are in the market are very similar to, or if not exactly the same pixels which we have taught to you till now. So if you can do a 40 pixels, you can write in your CV from here onwards that experience camera design. Good. We'll stop now and we'll meet in 15 minutes from now. Okay? Thank you. Okay. You can hear me now? Okay. You can make these clamped at the two beams, and the resonators could be going up and down in the torsional mode. The mode of equations remain fairly same. Let's analyze one of these in a bit more detail. Now, out of plane motion is easy to understand. Essentially, you are seeing something going in and out of plane, but it's slightly difficult to excite and measure. The way to excite a number of large excitation is basically you take a resonator chip, put it on a piezo transducer, and then shake the whole chair. If you shake the whole thing, they start moving on their own. The one which is slightly easier to appreciate for early analysis would be the in-plane motion. Things are moving. So we have got a plane, I have built a resonator, and the resonator is moving in the same plane as my substrate. Okay. A very simple way to excite this electrically would be something of this sort. You make a spring, you make a free mass. I hear a noise. Do you hear a noise? This is electrical engineer's problem. We can't live with noise, right? Okay. And then if you have a fixed electrode, if you just apply a voltage between these two, what will happen? So that's metal, there is a spring here. If I apply a voltage on this node, what will happen here? There will be electrostatic pull. This looks like a capacitor, right? Two metal plates. If one metal plate is free and the other has got charge, what will it do? There will be electrostatic force trying to pull it towards itself, right? Two charge have got electrostatic, first law of electric energy you might have read about is charge divided by square of the distance is proportional to that. Okay. So this electrode will try to pull this electrode towards itself. That looks like your excitation force. Now as it tries to get this side, the spring will try to have the restorative force. It will try to pull it back. And now you can see why this thing will oscillate in between. Okay. If we apply this electrostatic force, if it's a purely DC force, it will be entirely pulled in due course of time. If it's an AC force, a sinusoidal AC force, the moving mass will move up and down. Okay. And the amplitude of this mass will then depend on if the applied sinusoidal force has got the same frequency as the resonance frequency of the system. Now electrostatic force is a kind of weak force. It's not a very strong force, right, compared to other mechanical forces. So often a single parallel plate finds it very difficult to provide enough excitation, particularly when we are making small resonators. Remember, our parallel plates, everything is being quite small. So we often do these interdigitated finger-like structures where we are increasing the force of excitation and increasing the total force by having large number of such fingers. Okay. The principle of operation remains the same. You have got electrostatic pull between the resonators and it's going up and down. So here is an example of my postdoctoral work. It's a very large scale resonator. So you can see these the MEMS was also very noisy. It made my life miserable when I was working with it. So it has got 4 large bond pads in between. This is to connect electrical signal to it. The reason why I like it, I can electrically excite it and electrically measure it as well. And we'll show you how I can electrically excite it and measure it. Now, the way it is designed, I think I should stand up and have a talk. The way it's designed is these are the springs here on the 4 corners. Okay? And then we have a moving mass which is all around this structure. And you can see there are these sawtooth forms, right? So if you look, there's one sawtooth here with loads of fingers coming out. That is the still part. Anything connected to the bond pad is the still part. It's not moving. On the other side, there's another sawtooth part which is connected to this mass which is going all around. Okay? It's a bit tricky. And here we have got more of these sawtooth fingers. So everything connected to the bond pad. So from each bond pad, I have got a line coming out which is connected to one side of the sawtooth, another line coming out. And the other side, I have got this line which is freely moving. So many sawtooth waveforms we did only to increase the number of the amount of electrostatic force. Here, each one of these about 2 micrometer in dimension, and they were made in Kinetic Foundry in UK. And the gap is of the order of about a micrometer. Okay. The idea is, as we apply electrostatic force from 2 of these, this whole structure starts moving. Okay. So I apply 2 of these to apply an electrostatic force, but then I use another 2 of these to measure by how much is it moving. Okay. And we'll see in a second how do we measure this structure. Now, fairly large resonator, the overall size is roughly 100 micrometer by 100 micrometer, whereas each individual resonator is just a few micrometer by about 2 microns. Okay? Good. Now, then comes the next question, which is how do we talk to resonators? By talking to resonators, we mean how do we excite it and how do we measure it? The excitation of resonators can be through one of many different forces which are there in nature. We could do electrostatic excitation. I just saw an example of this is an example of an electrostatic excitation. We could make the resonators to be of magnetic material, and we can use a magnetic force to excite. Piezo is shaking the whole thing. We could do a thermal excitation as well, apply heat to it to start moving. And then comes the measurement part. If something is moving, you can always do an optical measurement, right? You can see that, you can visualize it, you can take a picture of it. But if it's moving at a very high speed, a megahertz, then taking pictures is slightly tricky, particularly when the structures themselves are fairly small. In such systems, we use some sort of laser Doppler velocity meter. So in the sense, we shine a laser light on it and then look how what's the time it takes for the laser beam to go there and come back. And we measure velocity using a laser beam. The problem of optical measurement is you need an external device to measure this tiny device. You need a laser source and all of these things to measure. So they're very tricky to integrate. At the end of the day, we want a small scale system which we can sell into the market, not necessarily a system with which you need to buy an instrumentation as well. Just the way we could excite something magnetically, we could also measure it magnetically. If there's a magnetic flux changing in the field, it could become a transformer-like thing. Okay. We could also do resistive measurement if the resistance of the things are changing. And I will show you an example of thin films, when you stretch them, their resistance changes. So if things are moving up and down, the resistance is changing. So we just measure the resistance change in these materials, and that gives us an idea of the motion which is happening. Now, to give you an example how this circuit worked, remember the big resonator which I showed you earlier. So what we had a moving structure which is all around, and plus has got all these interdistated fingers, and that structure we have grounded. So electrically, it looks like this grounded moving structure which is moving between parallel plates. Then two of these plates we are using for excitation. So we basically apply a force here, okay? And we are applying a DC force plus and minus an AC force, okay? So on one plate we have got VD plus VA, on the other plate we have VD minus VA. Okay. On the other plate we are looking for its motion. So essentially it looks like a big plate. From one side we are exciting, on the other side we are measuring how much it is moving by, okay? Because that will tell us how far we are from the resonance frequency. And then the rest of the circuit is fairly simple. So what happens, you guys are getting a slip, whatever that means. Huh? Food coupons, I never don't get food coupons. That's not nice. All I have to eat is this mirchi bhaji, chili bhaji. They're not even doing any work. Okay. What's the current in a so that's a capacitor, right? Essentially, you can see there are two capacitors, the moving plate and the fixed plate, and the moving plate and the fixed plate. Let's try to understand how it works. What's the current in a capacitor? C dV dt. Now that's an answer you give when you have been an electrical engineer for 4 or 5 years, which most of you have been, right? You have passed your bachelor's, so you have forgotten the fundamental question. If you ask a first year electrical engineer or first year engineer, what's the answer they give? What's the current in a capacitor? You had assumed the capacitance is constant. Yes? As my middle plate is moving, what is changing? The capacitance is changing. Now look at this circuit here. This is an op amp, right? OTA. If I apply a V positive on the positive end, by virtual ground I will get the same voltage here. So the voltage applied is V0 here and another V0 here. So DC voltage is fixed in this, in the readout side. So let's again ask the question, what's the current in a capacitor? How do we get that C dV by dt equation? CV is the charge in a capacitor, and we say dq by dt is current, so we say C dV dt. But the actual relationship of current in a capacitor is C dV dt plus V dc dt. Are you with me? Or do you want to do it on the board? Right? So here we are doing the other way around. We are keeping the voltage same, and we are measuring as this thing moves up and down, what happens to the capacitance between this plate and this plate? That changes, right? And the relationship of that change will be, it's a parallel plate capacitor. What's its capacitance? Epsilon naught, epsilon r, area divided by distance. So as my distance is going up, my capacitance, when my distance becomes smaller, my capacitance goes up, and vice versa. But there lies a problem. It's a non-linear relationship because the distance is in the denominator. Right? So it's not that the distance changes by 1 micrometer, my capacitance is also changing by 1 unit. Agreed? Okay. In this case, it changes by 1, but if it changes by 2, my capacitance changes by 1 by 2. Okay? So it's not a linear function of distance. But as you will see, by doing a positive and a negative biased excitation, I kind of get a linear function of that movement. So the current produced here will be V, voltage which I have applied is V naught, times change in capacitance with time. That current essentially passes through a resistance here, and I get a voltage on both sides. I then take the difference of these two voltages through an instrumentation amplifier. So rest of the circuit is fairly simple. Okay. Let's look at the excitation side. What happens here? How does this thing move? So I'm applying a DC voltage. I will need a minimum DC voltage to let the thing move, and then I am applying a sinusoidal, small sinusoidal voltage. Okay. If my small sinusoidal voltage is having the same resonance frequency as the system, this will start moving up and down with a more magnitude. Now, it's not always the case that will move by itself. What stops things from moving? There is a Newton's law which basically says nothing moves on its own. Okay? But in real life, we get something else stopping things from moving. Well, sorry. If I push something, it doesn't want to move. What is stopping it from? What is stopping this from moving? Sorry? Gravity is in this direction. I'm moving it in this direction. So gravity and mass will be related. Mass causes the weight. Okay? But weight is in this direction. If I'm applying a force exactly 90-degree opposite to it, think of it the other way around. Something is moving. What is trying to stop it? A car is moving on the road. What tries to stop it? One is the road friction, right? What is the other thing which is trying to stop the car from moving? Air. Well done. Which is forces on a car. Okay? And then we will try to calculate which one is the bigger. So, road friction, what is it dependent on? Mass, right? Road friction is dependent on the weight. Whatever weight is applied, it's a something multiple of that. And we put, but cars have got a very unique thing. They are not a solid rigid structure. The things which are moving are circular. It's the tires, right? And they have quite a low friction coefficient. Whereas what is facing the air? The whole front of the car. So you will realize when we do the maths, till a certain velocity, which is fairly low velocity, is the road friction which causes the problem. But after that, it's the air which is a bigger problem. Why do you think we make cars in aerodynamic shape? They are made in a something like an arrow kind of shape, right? It looks like this. Or even your high-speed trains, what's the name of the high-speed train in India? Vande Bharat or Namo Bharat. They all have got a frontal design like this, right? If it was a road friction, why do they have this design in the front shape? And who gives the drag force? Air, right? So essentially what you're trying to do is you're trying to minimize the surface area which is in touch with the air. This is why, missiles or bows which are diagonal, they go faster. Try throwing something of the same mass which has got a flat shape. Right? Or you have played frisbee, right? You've tried, or you try throwing a plate, food plate, on its edge side versus its front side. Which one will go further? The edge side. Why does it go? A surface area to the air is limited here, right? So the viscous drag which the air is putting on it is low. So we just realized air is a bad thing. We all agree air is a bad thing? We also breathe the same air, or else we will not be a human being if there is no air on us, right? But for motion, air is a bad thing. We'll come back to this in a few seconds. So that was an example of electrostatic excitation and electrostatic readout. Here is an example of resistive readout. So these are piezo excited. So this is a graphene resonator which have got 4 bond pads on the 4 sides. And this looks like an H beam. So on the 4 sides it is held. And as we shake the whole thing, the resonator starts going up and down. And as it goes up, essentially it goes like this. The upper layer is stretched and the lower layer is strained. But this is graphene. It's a one atom thick or few atom thick structure. So as it goes up and down, its resistance changes. So all we are doing is we are measuring the resistance between these 2 plates. And that gives us an idea of the motion. Now, if I measure the resistance, I'm exciting this with, say, a sine omega t, right? 5 sine omega t or a cos omega t. I'm exciting the piezo with a cos omega t. What you would see is that the motion will be on the same frequency at the excitation frequency. And hence the resistance change which I will be measuring will also be on the same frequency as the excitation frequency. So resistance will also be R times cos omega t plus phi, okay, where phi is the phase delay introduced there. Here's another example of a circuit which we made with Professor Deepak Uttam Chandani in Strathclyde University. This is electrically readout. Now I have got 5 such cantilever beams. Why we made 5 we will see shortly. But these are freely hanging, so they're moving up and down. And in this case, we basically applied a laser beam on top on one of these and then looked at how much movement it is taking place. So this is an example of piezo excited, resistively measured or optically measured. Now, in the 5 slides, I have talked about 5 different ways to excite these things and 5 different ways to measure these things. I have also shown you 5 different types of resonators. Now, this is one of the problems why these things don't have market success. Virtually every research laboratory have their own unique design which can only be made in their design process. We discussed the other day, microfabrication is costly. The only way you recover money in microfabrication is if you make a large number of samples or a large number of different devices using the same technology. Here, each technology is only being used for making one type of device. So, unless that device has a huge market, despite the fact each device is very good, very highly sensitive, it doesn't make a breakthrough in the market. And that has been a problem with microelectromechanical system or nanoelectromechanical system forever. Chip designers, we make loads of money. Our devices are fixed. We can't do anything with devices. If tomorrow you go and ask, can you give me a different VT process, the foundry will say, get lost. Design using what we have. 3 different VTs, design it using. Whereas MEMS people, they keep on tinkering with their process to get the optimal response. And the other issue with MEMS is damping. All mechanical devices do not want to move. And when being moved, they want to stop their motion. Okay? We are not free space. Once I start something, it will keep on moving. All devices which are here there are n number of forces which are acting on it to stop it from moving, air being one of them. And it's just not one sort of damping we have. We have thermal damping, we have acoustic damping, we have n different types of ways in which a device is stopping it from moving. So, let's take the example of our resonator which was going up and down. There is air between my my films, right, which is stopping it from moving there. My spring themselves have got some thermal stiffnesses. They don't want to move too much. All of these act as if they are a different quality factor in the system. All of them look like they are, for each resonant system, have got a dampening system, and many of these damping systems are coming out parallel. So, overall damping looks very much like there are many capacitors in parallel. If you look at the type of damping, you get damping due to one and anything which you are doing. So, depending upon the shape and size of your structure, for the same situation, some shapes have got lower damping than others, depending upon which material have you made it from, which alloy have you made your material from. While making, have there defects in it? What's the air pressure, what's the temperature, what's the frequency of operation, and how you have gone about making it. All of these lead to some viscous damping or some stopping of motion So, let's look at some of the bigger ones. We can't analyze all of these because that will be very much into material side domain. We are not going to analyze. Very soon we will see how we can convert all of these mechanical properties into an electrical circuit to measure it. Because I am not going to analyze the individual damping performance, but I just now saw this relationship where damping due to each one of these components, this looks like a parallel combination of capacitors, right? Or is it, sorry, a series combination of capacitors or a parallel combination of resistors, right? Yes, no? If we have resistors in parallel, this is how we add them, or we have capacitance in series. So, this is already giving me an idea. Rather than designing mechanical system as mechanical systems, what if I transform their property into equivalent electrical property and design the whole system as an electrical system? There are few advantages of doing this. We know how to simulate an electrical system. You are working on cadence, we have got SPICE, we know KCL, KVL. They are comparatively easier than to analyze each one of these individually. Anyway, Let's look at the big damping things which are there for us. One is fluid damping. Now, almost all resonators on earth are moving in fluids of some sort or the other. Air is also a fluid, right? So either we are moving in air or we are moving in a liquid medium. And here, my surface interacts with the fluid, and my fluid is stopping my surface from moving. Okay. Now, the effect of this damping, the fluid damping, is generally proportional to the velocity, not acceleration. The faster I move, more I am being damped. Car scenario again. Once the car has been started, the road friction is very low. Right? You only need to put gas to increase the speed. Actually, you still need to put gas even to go at a constant speed. Do you do? Or else the question lies, if you need energy for acceleration, you need to apply a force for acceleration, right? Force is equal to ma, not for maintaining a velocity. But in cars, even to maintain a velocity, you still need to give fuel to it, or else it dies on its own right. Now, the quickest way to solve air-based fluid damping is actually to take these sensors into low pressure. So you can put them in low pressure chambers, reduce the atmospheric pressure, there is less air there, there will be less damping. So number of experiments which we have done in past, including those resonators which I showed you, were done in a kind of a vacuum chamber, not pure zero vacuum, but somewhere where the air pressure has been reduced significantly. And there lies the immediate concern with these devices. The devices work brilliantly, but if they are only going to work in low pressure, they will not be very useful for real life experimentation. Now, but anyway, you can still say, okay, we do the experiment, the relationship there, and then bring it down to low pressure to measure it. So till a critical pressure level, low air pressure leads to low damping. After a certain pressure, the fluid damping is independent. It doesn't depend on this at all. Then there is a squeeze film damping. Now remember, we are making our resonator on a substrate. So essentially, I would have made it something like this. There is a structure which has allowed it to move. So I would have removed everything from here, hold it there, and then allowed it to move this way. Or it is held like this, and I'm asking it to move there. So in between my resonator and the substrate, there is a thin film of fluid, air. Now that's the air which is very difficult to remove, even when I'm taking it down at low pressure. And it leads to damping, it leads to stiffening of the structure. The structure doesn't like moving. And it's affected by a number of factors, things like what's the size, how much is this structure, how much is the gap between my substrate and the resonator. If I have bigger gap, that will be low because squeeze film damping will not be there. What's the thickness of the fluid, how much radiation we are going. Okay. Then we have structural damping. The structural damping happens is the second order damping relationship. So as my things move, they cause stress and strain in different parts of my resonator, which then leads to heating there. Heat is a loss mechanism. Energy is being lost if something is being heated. At the same time, there might be some places which will be cold compared to this. So there's cooling taking place, which is also a loss mechanism for him. So once I have got a hot structure on one part of my resonator and a cold structure on one part, I've got a heat current flowing between these two. It looks like a potential difference. Okay. So there again, I've got a damping mechanism. Then our clamping and anchor damping, I'm clamping my structure to something before I can move. It's not a freely moving structure which is moving. It's held from one side, either on this or on both sides. There is an elastic wave moving in my resonator which sees a boundary here on the clamps. It cannot move beyond the clamp. So this looks like a You know, we have in communication waves, we have got signals bounces out, the reflection of the signal. So that leads to structural damping. Then you have got material damping. Ideally speaking, we would have made our resonator perfectly from the same material with no air gaps. No, it will be a smooth structure, but we know structures won't be smooth. There will be some rigid structure. And this would lead to damping on its own. Now, this is the most difficult damping to model. Okay. It can be limited by processing steps. You can heat the structure, make it as smooth as possible. But at the end of the day, it is still fairly difficult to model. It depends on the operating temperature a wee bit, but just a little bit on that. So what we have seen is we can make a moving structure, but it causes quite a lot of issues in damping. And I learned it the very hard way. So remember, I made those resonators. The resonators were made to measure very tiny mass. And we could measure very tiny mass. So on the things we are moving, we could deposit a small amount of platinum on them and then measure the exact amount of platinum but just by looking at the frequency shift, and the device worked brilliantly. Then we thought, oh, that works brilliant. Why can't we use it as a biosensor? Remember, we did the biosensor calculation. So I took my resonator to a colleague in Ireland, and they said, but our solution is in liquid. We have got this mRNA or bacterial solution in liquid. And so we coated our sensor with some reagent, and the idea which I thought was, okay, we take my resonator in the liquid, let the reaction take place, let its mass change. I will bring it back. I'll put it back in the vacuum and measure its frequency change. So I measure the frequency of resonator, resonant frequency, take it out of vacuum chamber, let it react, bring it back to vacuum chamber, and I will be happy, done. The resonator never worked after taking it into liquid. We tried everything, applying high force. The classic way to move my resonator was to poke it with a hair. Remember, this is 100 micron big. So our hair is 100 micrometer thick. So I used to go about either plucking my own hair or asking people for a sample of their hair to poke it. It will not move. After much effort, what we realized, that there is something called surface tension of water, which we electrical engineers have completely forgotten. Do you remember surface tension? It makes those air bubbles kids play with, right? It forms an air bubble. We never see that in electrical engineering. We had bubbles formed between this structure and the substrate. And now because my structure is very small, the surface tension looks like a very high force. And I could not remove that liquid. Whatever I did, I heated it, I took it to low pressure, that liquid just got stuck there and it will not leave. And this area we're talking about is roughly 100 nanometer thick. That's it. It's a very tiny amount of liquid. But for that resonator, it's a solid resonator, that liquid surface, that bubble had very high force that will not allow it to move at all. So forces which we can ignore at mega scale all of a sudden become very important at micro scale. So far so good. Still, having said that, a number of these devices are used commercially. We will talk about gyroscopes a bit later, the ones used in cars, how they operate. This is more of a research line direction. The other thing which happens when you make devices very small is they start becoming nonlinear. Our entire electrical engineering theory is based on linear control theory. Agreed? What do we do when things become nonlinear? How do we analyze nonlinearity? So say that's a linear system wherein that was my original resonance frequency, something happened to the system, it moved. But the shift is still a very linear shift. It still looks like a resonance system. What if it starts looking like this? That's not a sinusoidal frequency response of a sinusoidal system. Okay. Or let's take a system like this. Ignore wherever this response comes from. If you ever see a response like this, what do you do? And we have seen a response like this in transistor responses. So how do we analyze this as electrical engineers? We do one of these two things. We either say, okay, sir, this is nonlinear, but if I only operate it till this point, it looks like linear. So we'll only operate it in the lower region. There it's linear. Or we say, okay, it's linear till here, from here to here it's linear, and from here to here it's linear. So we do piecewise linear approximation. Okay? Now piecewise linear approximation works brilliantly, but then you lose all the good things which you get from nonlinear dynamics. Nonlinear systems by themselves have got very beautiful properties. So let's look at one of these properties. And we can do maths very easily. So remember how we analyzed pendulum in our high school days. Remember, you did the pendulum experiment in your school, right? Or have you seen a pendulum in your life? Move it on one side and it keeps on rotating. Okay? So let's remember the high school maths of that time for a minute. So what did we do? We said we move it up. What's the force acting here? So this force is tension T. This force will become T cos theta, if this is theta. And the restoring force which is trying to bring it back will be T sin theta. Agreed? And then we did this wonderful thing of maths. We said if theta is small, sin theta is same as theta, right? That's the Taylor series expansion. The first term is theta. What's the full Taylor series expansion of that? We have got theta minus theta cubed by factorial 3 plus theta 5 to the power factorial 5 and so on and so forth. We said if theta is small, you can ignore all the higher order terms. What if theta is not small? Or what if my pendulum is too small for theta to be ignorable? If my pendulum is just this, no, just this much. At this point, this looks like a big angle, isn't it? So my standard equation, if you remember, came something like, we had an equation like this. This was a second order differential equation. It's the same as the mass spring equation which we get, which is mx double dot plus bx dot plus kx is equal to the applied force. And this linear function came because we had assumed this theta to be. So let's take the first order nonlinearity, theta cube. Okay. Again, from mass spring system, we generally take the cubic form because the square law force, what do we say? Force is equal to minus kx. Okay? Actually, force is equal to k times minus x because we are moving in the opposite direction to the force. So if we had a square law nonlinearity or second nonlinearity, then the force would have been k minus x, that's the linear force, plus some k2 minus x square. Minus x square becomes plus. So if we had the square law nonlinearity, which we do sometimes, but for the first order mathematical operation, it looks like I'm pushing the beam on my side and there's more force taking it further on this side, which is a bit counter to nature. Nature should try to restore, right? If I'm pushing it, if it goes on there, then it becomes cylinder. So the first force we see is the cubic. Cubic is in the same direction. Minus x cubed is minus. So we now get a relationship something like this, plus kx plus k1x cubed is equal to some sinusoidal force. What will be the solution to this? So that part you can solve every maths course teaches you how to solve a second order differential equation. All I have done is I have added a simple nonlinearity to it. Just one cubic term, nothing else. I haven't done anything to the damping yet. Okay? How will you go about solving this? Now, here's the fun part. Most nonlinear dynamics equations are unsolved. There is no closed form solution to this problem. What you can do is you can do perturbation and find an approximate solution. You can write a MATLAB code or a Python code to time series simulate it by using Newton-Raphson method. You cannot find analytical solution. So this problem was studied first by Duffing, a German mechanical engineer. And he looked at how mechanical structures move when they have got nonlinearity in their spring constant. There could also be a nonlinearity in this term, the damping. Damping is linear here, it's directly proportional to velocity. Right? We could get a cubic order nonlinearity as well, or we could get more written as something like this. Because if you have an x dot cube and you are doing dx by dt, this looks like an x square dx by dt, right? X cubed dx. So we get a relationship like this where you have got an x square x dot term and x term by itself. This kind of nonlinearity was studied by an electrical engineer for the first time by the name van der Pol in light bulbs. And these two gave birth to the field of nonlinear dynamics. The entire field of nonlinear dynamics, which is studied quite a lot by physicists and mathematicians, rose out of work of our field, and we have forgotten all of it. We don't study light bulbs anymore, right? We don't, the vacuum triodes we don't study, right? But these are very interesting equations. Duffing and the van der Pol. Van der Pol is a very interesting equation because van der Pol can make an oscillator. So a classic oscillator, I'm a bit diverging from the topic, but I really like this thing because I had to learn this as part of my postdoctoral. We never taught nonlinear oscillators in our undergraduate or even in graduate studies. We only taught linear oscillators. So linear oscillators produce this as a response, a sinusoidal response. Okay? If you have a nonlinear oscillator, you might get something like this. It looks like the RC charging, rapid discharging. You could get, so depending upon the initial condition or the excitation voltage, the same nonlinear oscillator will give you a different response. Now, this is written in the literature, but it so happened my wife noticed it in one of my research papers, and that's how I got even more excited by this. My wife is a medical doctor. She has, well, I shouldn't say she has no knowledge of maths, but generally they don't have a love of mathematics as we do, right? And she saw similar relationships, actually basically doing this and then quick discharge, rapid discharge. And so like that's the waveform we look of human heart, because that's how the human heart goes. And then I would, yes, van der Pol oscillators are used to model the human heart. And this very simple relationship, wherein you just bring nonlinearity to the damping term, models a large number of things in nature. How do we walk? Quick, start, charge, start, discharge oscillator. It's a van der Pol oscillator, slit a slight. How do fishes swim? Charge, discharge, discharge. They are oscillatory motions, aren't they? Now, funny thing is this. The reason why I'm talking about nonlinear oscillators, look, nature made good use of nonlinear motion. Heck, we walk using that. Our heart behaves that way. And we are saying we do a piecewise linear approximation of this because we know linear control theory. We don't understand nonlinear control theory there. Okay? So there is a rich amount of literature on nonlinear control systems which can be used for sensing purposes. I mean, think of it this way. That is the response of a Duffing resonator. If I put kx dot, what happens is so in a linear resonator, we go up and we go down in the same way near the resonance frequency. The Duffing resonator, it goes up, saturates, and then has a rapid fall. So if you are thinking enough, you might think of we could make a resonator, or we make a sensor where when you're operating here, and if anything changes, the response immediately falls down. That's a highly sensitive sensor, if we could control the nonlinearity. Okay? So if we get time, I will talk more about nonlinear systems. They are very rich, very dense, and quite frankly, I've spent about last 6 or 7 years trying to understand them. I only understand a little bit. We have published some decent papers on it, but we only understand a little bit on this thing. So that is what I was working on, looking at the nonlinear relationship of the pendulum. So pendulum moved further also behaves like a nonlinear system. This is the Duffing nonlinearity. This looks like, so it could be positive or negative. And in real world, it looks like my spring has hardened. So a linear spring will have the same force as you push further. A hardened spring, you push farther, it will try to pull it back. Or a soft spring will allow you to pull further back. So nonlinearity here is looking like my spring is a hardened spring or a softened spring. And to show something interesting, we have got this hysteresis kind of response. So a simple resonator will behave classically in this form, wherein you have got a symmetric response in the frequency domain. A hardened Duffing will be bending on one side, and it will also show hysteresis in the sense if you are going from positive to negative, you will follow this path and then fall down here immediately to come here. And if you are going from high frequency to low frequency, you will not go up immediately here, aka, so here you would go here and then drop here. But if you are coming backwards, it will not go up here, it will go up till here, then move up and then go down. And the same relationship is seen in the softening response as well. Okay. Similarly, as I said, you could have nonlinearity in damping, and that would lead to a van der Pol type of relationship. Despite 100 years of nonlinearity work, we are still barely understanding nonlinear system. So both of these systems can go chaotic. What's a chaotic system? How do we mathematically define a system to be chaotic? You have heard the word chaos. We always have chaos in our society, right? But what is a chaotic system? So a chaotic system is defined as a system which, for a very little change in the initial condition, leads to a big change in the final condition. Okay? So mathematically, universe could be a chaotic system. Had the Big Bang happened slightly differently, we might be completely different. Okay. Weather pattern is often called a kind of chaotic system. You've heard about this butterfly in China theory, that if there's a butterfly flappers its wing in China, that might lead to a hurricane somewhere, because one thing is related to another thing and so on and so forth. Both of these systems can be built into a chaotic system. You excite them with enough force, they will lead to a different response in different excitation. Good. So we have talked about single structures. We have talked about nonlinearity in the structures. We have talked about different type of excitation and measurement. Remember, I'm not going deeper in any one of these because I'm giving you a broad overview of the whole thing. One last thing which I would like to talk about, and let's see if we have enough time for it, because I might have to go and say hello to someone, would be coupling. Oh yes, we have enough time. Still now we are looking at one resonator. Each resonator is a few micron. Why make just one resonator? Why not make more than one? We make more than one transistor on a chip. Now that's one of the reasons why we have been successful in the electronics world. We can make 1 billion transistors on a chip. The microelectromechanical system world is still very much stuck at one or few sensors per chip. You make only one gyroscope on a system. This is where I also spend a lot of time working on our research, wherein we generally don't like mechanical coupling because our system is moving nicely. There's another system which starts moving on this side. It will couple its response to this, and my movement won't be nice anymore. So generally speaking, we don't want any coupling. We want our system to be pure in its own environment. A very good example, have you guys done double pendulum experiment in your school? You take two pendulums, connect them with a spring, what happens? Never done experiments like these? You know what? Let's make a double pendulum in the afternoon. Okay? What do I need? Tennis balls. Anyone has spare tennis balls to give us? Don't worry, I'll go and buy the double pendulums because they are very nice experiments. So, if you take two pendulums and connect them with a string, there is only two ways the pendulums will move, whatever you do. They will either go together or they will go in opposite direction. You excite them here, you bring them here, leave them after a few minutes, that's the natural motion they will come in, as long as they are linear systems. Okay? You take three pendulums, there are only three ways they will move. Either all three will go in the same direction, or the middle one will remain fixed and the other two will go up and down, or the other two will go in the same direction, but the middle one will go square root 2 times more in the opposite direction. Now these motions are fixed by a very decent maths we teach to all our students. Remember eigenvalue and eigenvector. We take matrices, we take eigenvalues, we take eigenvectors. So if you consider two pendulum, it looks like a 2 by 2 matrix of a system. Okay? It will have two eigenvalues. The two eigenvalues are its two resonance frequencies. It has two resonance frequencies, one in motion and one out of motion. And the amount by which it moves by, that is its eigenvector. Okay? It took me 6 months to figure this out. Once again, we have done eigenvector and eigenvalue, but quite often we do not correlate it with something. In mechanical engineers do it. We unfortunately don't do this thing. So I will just do analysis of one system to show you why it is interesting. So remember those big resonators I was making? We actually made 5 of them coupled with one another. So essentially, what I wanted to see is I know this motion happens if I take two pendulums and I just move one pendulum, in due course of the time the other one also starts moving. If I move one, it will move and it will slowly make the other one also move, and in the end they both will move either in phase or they will move out of phase. Can I use the same logic to make an array of sensors where I just have to excite the first one? Otherwise, if I make sensors, I need to excite each sensor, I need to measure from each sensor. But I know from this pendulum thingy that I can excite all of them. So can I make an array of sensors, just excite the first sensor and hope all of them start moving? The other thing which we know is the frequency at which they move is the eigenvalue of the system. If any one of my resonator changes, think of a matrix, right? If you have a 5 by 5 matrix with elements only on the diagonal or an off diagonal. If any one value changes, my eigenvalue changes, right? Now, my eigenvalue is the resonance frequency of the system, which I can measure from the response of any one resonator. Think again, two pendulums. Actually, you know what? Do I have a theory of two pendulum? Yeah, I've got two pendulums here. So these are two mass spring systems, okay? Two mass spring system, and I have coupled them with another spring. So in the end, what they will do, they will either go this or they will move together. So if you now look at their frequency plot, we will have two resonance frequencies, one in which they are moving in plane, they are moving together, and one in which they are moving out of plane. And both resonators will have, the frequency will remain the same at which they move in or out. The amplitude might be different depending upon what's the individual sizes of the resonator. Their frequencies will always be the same. Okay. Now, if something happens, let's say my resonator 1 has changed. Okay. You can see the resonance frequency shifts. So, blue is my original response and red is my shifted response. The same thing happens when resonator 2 changes. So, essentially, if I have an array of resonators, I can measure the entire resonance frequency from the response of the first resonator. Then if my fifth resonator changes by measuring mass or stiffness or something, the entire eigenvalue of the system will change, which I can still measure from the response of the first resonator. So I can have an array of sensors and just measure it by the response of one resonant system. And I will show it to you here. This is a 5 resonator system. That the solid lines are the frequency response to various frequencies. You can see it's in kilohertz, but nothing has changed. That's its natural response. At one frequency, it has got low amplitude. At this frequency, it is high, so on and so forth. Now I go and change the third resonator. Oopsie daisy. I think that is telling stop talking. It's lunch hour now. Is it lunch hour? Almost? No? Let's carry on till Professor Muralidhar comes in and drags me away. Is he already there? No. So when we change the third resonator by putting a small mass on it, and we are still measuring only the first resonator, we are not measuring the third one at all. The frequency response of the entire system shifted. This one did not shift by much. This one shifted by a large amount. This one shifted here. This one shifted here. This one shifted here. Okay. So just by looking at the frequency response of the first resonator, I can tell which one of these resonators have shifted. We also did this experiment with this coupled system. We have got 5 resonant systems, and at this point what we did was, as you can see, we have cut one of these slightly. Okay. And once again we saw a change. If you can see the dashed line, we saw a shift in resonance frequency response from one resonator system. So this kinda allows us to make a mechanical multiplexer. What does a multiplexer do? It selects one of many. Now we can measure the response of an array of the system just by looking at response of one system. Now how do we do maths of this thing? So let's see what's going on in the mathematical part. If I write the equation of the first mass, I have got mx1 double dot plus kx1 plus, so kx1 is its own spring constant, plus then there is a k coupling, which is the middle spring. K couple, and that spring sees the motion which is difference between the x1 and x2. Still a linear system, okay? So x1 and x2. The second one has similar equations, but now it has got a coupling which is x2 minus x1. It sees the other relationship, okay? If I write this as a matrix form, I can write a mass matrix M where just M1 and M2 on the diagonal. There is nothing on the off diagonal term. And I can write K as a stiffness matrix. So the stiffness matrix will be of this type. So what's related to x1 in the first equation? I just have K plus Kc. Related to x2 in the first equation is just minus Kc. Related to x1 in the first equation is Kc plus Kc. If you expand this term, think of expanding this matrix, The first line of this will be m1 times x1 double dot plus 0 times x2 double dot. This side plus k plus kc times x1 minus kc times x2. That's my first equation. The second equation similarly is m2 times x2 double dot plus minus kc times x1 plus k plus kc x2. So this matrix represents that equation. Okay? Now, if you remember, that equation looks like the starting situation of the eigenvalue relationship which we teach to our students, right? And I can write this as you can take m as m half, or even if you can normalize the whole m to become 1. We can take all masses to be 1. This becomes the eigenvalue relationship. It's the eigenvalue of this matrix which then tells me at what frequency my system will move, and the eigenvector which tells me how much they will move by. Okay? If I extend this relationship to n such systems, then I will have a tri-diagonal matrix where all other terms are 0. Remember, because this element is only talking to its nearest neighbor. So if I have got a second element, it has got some response from the first element, is doing something to the second element. So I will get a large matrix which will be a tri-diagonal matrix, and the response function of that tri-diagonal matrix will give me the eigenvalue and eigenvector of these systems. So here is what my 5-element system behaves like. Remember, I made, right now I'm showing you just 3 for the shortage of space, but we made 5 such resonator system and we measure the response function. So on the solid lines we have got the amplitude response. On the dashed lines we have got the phase response. And as I said earlier, it can act as very good mass sensor for very small masses, as well as a very good stiffness sensor for very small stiffness changes. I will leave you shortly because the question here again is, MEMS world has always lived in future. They're always talking of new materials, new type of designing circuits. Each physicist and chemist has his or her own favorite material and favorite design. What people don't talk much about are how to design, what's the noise, what's the variability, what's the nonlinearity in the system. And this is where we as electrical engineers can contribute to this field from a research point of view as well. We don't want to change the material. We don't want to change the design. We want to have one standard. Remember what I did just now. I picked one design of resonator, and I said I will just make loads of copies of these and then see that as, because that way I don't have to redesign everything. I can't redesign everything. Design of each one of them takes a lot. Some of you might have done your courses on things when we teach what is accuracy, what is sensitivity, what is precision, what is resolution. Done that? And they are classic interview questions as well as classic examination questions. So we'll do that quickly as a revision. Remember, I did not start with those things. I started straight with camera design, because I know all of you guys have used cameras in your past. But we need to know some of these fundamental terms, because right now I was doing a qualitative design of the system. I was not going into the exact nitty-gritties. Right? I was saying, here's a pixel circuit, this is how it works. Here's a MEMS circuit, this is how it works, not necessarily on how to build them. So we will do that as the first exercise. The second exercise we will do would be to see how can we translate all these mechanical, chemical sensor into their electrical equivalent. Because if I can redraw that mechanical circuit as an electrical circuit, I can understand it. So I'm talking purely from electrical engineering point. And by electrical, I mean electronics as well. I know in India we separate electrical and electronics as two different disciplines. It's the same from my point of view. Right? So we will translate all of these mechanical circuits or mechanical systems or chemical system into an electrical equivalent and then design using the electrical circuit. Okay? Any questions for today? If not, highly recommended book will be Microsystems Defined by Steven Centuria. There are also books by Joshi, which is I have used, which is the EPJ. I've used the EPJ technical, the journal, EP journal on technical instrumentation for the MEMS, for the damping part of this lecture. And I have used some of the pictures from Micro Machines journal by Aplo Bhamid. Today we have gone through a little bit of microelectromechanical system from a resonator perspective. In future, we will also see them from a gyroscope perspective, from an accelerometer perspective. The sensors are not terribly different, but the design approach is different. Right now, we are looking at the individual motion, x or x dot. In future, we would like to see their acceleration. Okay? With that, I have been asked to stop at 12:30 today for a meeting, and I will stop now. I wish you good luck. In the afternoon, we'll meet at again 2:30ish, and we'll meet in the lab. Okay, we'll finish that design possible.
ఈ లెవెల్ పెట్టి ఏం ఏర్పడుతుంది?
ఇక్కడ ఏర్పడదు, స్క్రీన్లో ఏర్పడుతుంది నాకు. ఇక్కడ చూసేవాళ్ళు స్క్రీన్లో చూస్తారు కదా.
Okay. Are you okay? Can you hear? It's not okay? There's noise. Okay. Let's finish. I will do it for half an hour or so while they fix it. So one of the things which we saw in the morning was wide dynamic range pixels. And I knew the techniques which I have used to make wide dynamic range pixel. But that was a bit unfair. I should also tell you what other people do. Okay? Oopsie, not my computer. So classic problem is this. We have got, for low light, our pixel works fine. For high light, it integrates completely. Now we tried to make it as a logarithmic pixel, or we tried to do some sort of a linear and logarithmic together. That's not the only way you can look at the problem at. One thing which you could do is you could just increase the VDD. Right? If I give a big voltage sweep for it to fall down, I will get a high dynamic range anyway. Of course, increasing VDD is not advisable because that comes at the cost of power dissipation. So, other thing which could happen is what happens when this charge, this well fills with photocharges. When it saturates, what happens to charge after that? It spills, it goes somewhere else, either goes to the neighboring pixel or spills through the reset device. So one operation which we could do is to change the reset voltage every now and then and see if it gives it extra charge. There are many ways people have done. There is one circuit which is this. Essentially what you do here is you have got a separate capacitor to integrate the charge being produced by the photodiode. But you do not send all the charge. You send some charge to the capacitor, and then, now this is a common gate amplifier, okay? So what you do is you change the saturation level every time you reset it again. And you do something like this. For low photocurrent, okay, I get typical things. As soon as I saturate for the high photocurrent, I reset the pixel, so it starts again. Then I reset the pixel, so I get a waveform, comes some sort of a nonlinear compounding waveform for this. So the design which people did, this was Charles Houdini's design along with his student Decker. They had 8 analog voltages, and despite doing all of this, they only got 96 dB of dynamic range. Remember, a normal image sensor has about 60 to 80 dB of dynamic range. The human eye does anything from 120 to 180 dB. So from lowest level of 1, we can see up to 10 to the power 6 or 10 to the power 9 luxes. The other problem with these are, because it's a non-linear stepped response, how do we make color out of it? Is an open question for us. Other approaches people have done is don't change the saturation level. But what you do is you take the spilled charge and integrate it again. So you use the same diode, so you integrate first your normal value, and then after that you reset it and you integrate the spilled charge as a separate incidence. So essentially you do 2-stage integration, one for normal and one for whatever extra charge which is left there. There's another approach by Akahame and co-workers. What they did was they added another capacitance here, and the idea here was you have got a gate to the pixel, and then you decide what charge goes here and what charge stays here. There are multiple approaches on the same thing. The whole idea was we have large amount of photocharge that's saturating. Can I divide it into 2 chunks and do elsewhere? Here was another approach, and this was much simpler. Essentially what you do, midway during integration, you soft reset all the pixels, okay, and then restart integration again. So if you keep on soft resetting it, the pixel will never saturate. People have also tried putting 2 different type of photo devices, a photo gate and a photodiode together, moving charge from one to another, and that also increases the well capacity. So all of these type of high dynamic range sensors are called well capacity increasing sensors. So my diode has limited well capacity. We try to increase the well capacity by adding something or the other. The other approach which we saw yesterday was dual and multiple sampling. Take the same scene many times, and I went very, very quickly there. So question still says, how do you store these multiple samples? So Yarit Peck from Technion, she uses 2 capacitor banks, and each capacitor bank stores the output voltage from 2 different integration values. Okay. El Gamal from Stanford, he used an in-pixel ADC, and what he does is that he samples the pixels response at many times, but these times are exponentially increasing. So first he samples at time 2t, then at 2t, then at 4t, then at 8t, then at 16t. Okay, and then he integrates this as the digital response of this thing. There are also other people who are trying to find, rather than integrating each pixel, what would be the optimum time a pixel should be integrated. So initially we said, okay, 20 frames per second, we integrate it for 50 milliseconds. But if we know the average intensity in the scene, then we could change this integration time. So if we know our scene is dark, then we integrate it for longer. If we know our scene is bright, we integrate it for shorter. Now that could be done in many ways. There are circuit-based approaches, there are algorithmic-based approaches to find what's the maximum integration time in which none of my pixels will saturate. Acosta Serafini and colleagues, they try to find, they have got these integration slots. During the integration time, they check the pixel at every few instances. Is it going to saturate? Is it going to saturate? Is it going to saturate? If it is going to saturate, integration, if it's increase the integration window. The circuits are very similar to active pixel sensors here. All that you have is an extra SRAM per pixel to help you find these things. Belenki and co-workers also put a static and dynamic in-pixel memory to do the same operation. So we looked at changing the well capacity. We looked at doing dual and multiple sampling. The other approach which we could look at is this integration time control, right? We talked about where. So you can do it for all the pixels at one go, but that means, okay, I had one bright scene, one part of the scene, all my dark also changes with that. Okay. So another approach could be, we don't do for the whole imager, we do it for local areas. So now in this area my scene is dark, I integrate it for longer. In that area it's bright, I integrate it for shorter. So there have been couple of approaches wherein people have compared. So while it's integrating, you go and look at in each region till where my pixel has gone in, and then you adapt the integration time based on that. So here is one circuit which does that. I must confess this is slightly wrong. It's a PMOS level circuit, so it's exactly the inverted circuit. Remember, the pixel which you are having, you have NMOS on top and NMOS read. There's no reason to do NMOS. You can do a PMOS circuit as well. You can have diode on top. So here the diode end is connected to VDD, and then you have PMOS, and now you are resetting it. This is a PMOS, my apologies, to ground. Okay. So rather than the signal coming down, the signal will be going up now. So the inverse is also, generally we don't use PMOSs because they take quite a lot of area and they come up with, and they are slower compared to NMOS. There has been other alternative approach. This is Bridensal, wherein they reset every row at a time. They look at how much is a row taking to integrate. Okay, and they adapt the integration time of each row, and they store how much, at which stage this adaptation happened. Zarandi and co-workers, they put a latch inside each pixel, which then determines, is my pixel integrating for long or is my pixel integrating for short. Few other people have tried putting a column amplifiers in the column. I'm going to a bit longer because there's no use to study detail. They are all patented design for individual groups. But it's good to see that it's not just one approach. There are other approaches to solving the same problem. So here they have put a standard active pixel sensor, but in the column we have an amplifier to check what's happening to each pixel. And now you change the gain of the column amplifier rather than the pixel itself to figure out how it is going faster. In all of these integration time control approaches, we suffer from fixed pattern noise. And all of these we have difficulty on how do we reproduce color. You have to do additional pre-processing in advance to find what's the optimal integration time, You have to do additional post-processing in it later on. The next approach, and there will be just a couple of more approaches I will talk about, are approaches which look at, rather than changing the integration time, can we fix a threshold and see how long it takes for my integration value to reach there. So I measure a time. Okay. Right now, typically we are measuring voltages. Rather than measuring voltage, why don't we measure a time it takes to reach a threshold voltage? Okay. And there have been many such approaches. Essentially, you put kind of a comparator inside the pixels, see till where I have reached. So one of the pixels which I showed you in the morning, our design was also a threshold comparing pixel, but rather than fixing threshold, I was changing my threshold. So people have tried putting a threshold comparison in each pixel or in each row, and then you have got a reset register as soon as. So people have also tried a mix and match of this thing. So I measure it to a threshold in a frame. If my pixel has not reached it here, I allow it to integrate. If my pixel has reached midway, I reset my pixel. Okay. So if I reset my pixel, it starts from the beginning again. So many such approaches have been tried. The third approach is that of counting. So I only count how long it takes for my pixel to reach here. So as soon as my pixels start, I start a counter. I start counting the number of pulses. My pixel reaches here, that's the count I have got. Now, two advantage here, it's automatically converting to digital as well. Okay. So Ando and co-workers, they have put 1-bit ADC per pixel, and you can design a 1-bit ADC with series of inverters. They have used a 5 inverter. And the moment my pixel hits that threshold, it sends a high signal to be stored in a reset switch that I reached that threshold, and then I reset my pixel. So I do two-stage integration here. The design which I used to love quite a lot, which was very complex for me to understand, was David Stopa design from FBK in Italy. And they did a very interesting thing. They have 2 time clock pulses in the pixel. One which does fine measurement, another which does coarse measurement. So they have something like this when they are having 2 ramps, one ramp which keeps on going up and down, and the other ramp which is going at a more leisurely pace. And you are then trying to find where is my pixel reaching in both of these, between these 2 ramps. Okay. And by doing this thing, they are essentially recording the fine time and the coarse time which is needing to reach a certain threshold voltage. The problem with all of these is the computational circuitry required to manage the pixel is quite complex. So classic log pixels like the one which I showed you in the beginning, here is a log pixel with a bipolar junction transistor here rather than a diode, which people have tried. The classic log and linear log pixel is still one of the better ways of doing log approaches. Remember, when we were doing our tutorials, I talked about FPN correction. So this is my doctoral work. This is the circuit we had there. That's your diode, that's the switch, and that's the calibration current source. So that by controlling that current source, I can determine what current will flow here, and I can use that current to calibrate my diode. There's something else which we have done here. Remember, the model was y is equal to a plus b log x, and I kept on saying source follower does not have a unity gain, it has a small gain. So if my gain is small, any small error will lead to a big error. So one thing I could do is I could increase the gain in my output chain, so that even if there is a small error, it causes less effect. So this is one of the circuit we did. We did not change the pixel. The pixel remains as it is. It looks like a source follower plus row select. But on the other side, in column, we mirror it and we form a differential amplifier. So you have got a PMOS load there, this is matched, and then you have a column bias. We can design a differential amplifier to have a unity gain. A source follower will always have lower than 1 gain. So in your circuit, you all are having a simple source follower readout. If we keep both of them exactly the same, but rather than connecting this to VDD, we connect it to the load to get a differential amplifier performance, we can get a higher gain, and that reduces the our desire to improve on the gain mismatch. Just few more things before I let you go and do the lab work, and then we'll break again in half an hour to do the sensor circuitry work. Log pixel has a problem in low light region. As we start going, it doesn't go straight to 0. You see this smooth bend? So here I have got decent sensitivity. My X changes by something, my Y is also changing by that. In this region there is a smooth bend, so my X is changing but my Y is changing by a very little amount. So when I have got low light, log pixel have got low sensitivity. This is also the reason why we started doing lin log pixel in the morning, something which is linear, linear at low light, logarithmic at high light. And just before, I want to let you guys, this is the kind of response we received from our pixel. This is individual pixel measurement. Of course, it's a bit noisy measurement. So for high light, I was getting this low intensity. Then for medium intensity, remember it's saturating, but medium intensity and high intensity has not saturated at the same time. In our standard pixel, all of them would go all the way till here and saturate. Okay. So because I'm doing a logarithmic conversion, low light remains linear. After that I get a logarithmic response. So what I would advise you guys to simulate, if you are having difficulty in simulating your linear pixel, let's make it a log pixel, and that would be fairly easy to simulate. Okay, there is no time information to be fed, no current information to be fed. Of course you need a biasing circuitry, but you do have a just provide a photocurrent in parallel to your diode and you are done. Okay, so you know you have got a reset switch. Remove reset, connect the reset to VDD. That also removes one circuit which you need to draw in your layout, so life would be easier there. So I'll leave the circuit. So essentially we want this part of the circuitry. So now you only have one line going into the pixel, the VDD. Convert this to VDD, ignore the reset part, let's just have this part here, VDD and row select, and we are done. Okay. There will be one trick which you will have to do. This I think will be helpful to people who do VLSI here. It will not, it will show very high leakage current. The simulation by itself will show you very high leakage current. It took me a year to figure out why it does that. It's got nothing to do with heat generation. What's the photocurrent level we are seeing? Femto and picoampere, right? Remember the first day I was telling you SPICE, or the cadences SPICE, puts a resistor in parallel to every node to simulate the circuit. The resistor it puts is a 10 to the power 12 ohm resistor. Okay, it calls it G min. It puts in a conductance of 1 to 10 to the power minus 12. Now think of it this way, my current is 1 picoampere, okay, and I have got a resistor in parallel of 1 10 to the power 12 ohm. It already produces a 1 volt drop across that. So it's not the physical circuit which causes the problem, it's the cadences simulation which causes the problem. So to match that, we have to manually go and change the G min for simulation. I will show you how to change the G min in analog simulation later on once you have reached that. Okay, doc? So that's the lecture part of this theory, which also completes the tutorial side which we are doing in morning. Let's start the lab work. Okay. power supply we need to provide. The bias we need to provide to make the source power going saturation. This makes us simulate. This is the source power, right? This is MOS amplifier. We need to provide a current source to the MOS amplifiers to force it to be in saturation for it to work there. So generally when you take a current source, transistor, you apply a voltage and you see what's the current. All the characteristic is written as if you apply this voltage, this is the current you will get. We're doing the other way around. We don't know what that voltage is. We don't know what this voltage is. So what we're saying, okay, we don't give you voltage, we give a current. And then let's see what the voltage is. They're both related with one another. So we're giving it a current as a bias. Okay? And the photocurrent is what is making the effect of light. So photocurrent will be parallel to the diode. We say we can't do optical simulation, but we can certainly do a mimic the effect of light as if it's a current source in parallel to the diode. Okay? Each pixel is that. No, it's not emitting, it's capturing. It's taking a picture. Right? So light from this is coming to your diode, and diode is capturing that light.
Instead of three colors,
It is only doing one color.
this is doing one color. This taking this color, it's automatically it is processing.
No, nothing is processing here. All it is doing is, light is coming from this hook. It's just converting it into a voltage. That's it. The rest of the processing is for the next stage to be done. So light, first thing we need to do is convert light into voltage. Only then we can do something with that
The
process.
voltage we can
Convert it to digital, and then do any processing we want. So it's capturing the voltage, you can display it. You can capture and show it on a screen. Okay? Light. You're just capturing light, converting it to voltage. That's all the pixel is doing. Okay? Which pixel are you simulating? The active or the log pixel? Active pixel. Converted the active pixel into log, well done. No, this is a log pixel. Yeah, it's a log pixel. Zero is a big number. Very logarithmic plot. Where is zero? One atto, one atto, one. It's not a very logarithmic simulation. So I'm going to give it a doesn't matter if it's so this looks like a so till here there's a dark current. trick. So this often causes problems when you're doing layouts. If by mistake you have a small piece of wire and this big chip somewhere that just shows power supply and what happened is just label it. Don't hit a P, don't hit a P, just label it. L, L. So that basically says that this gets connected to that one. Okay? That's not input, that's power supply. This circuit needs a power. This is the power supply. This. Now when they are connect one of these to the out, they want to same 3.3 will connect to a row circuit as well. By shorting, and then one says that that's it. It's already shorted. So just label it, circuit assumes that this line is connected to this line. Okay. Right now, I shorted it together because there were lines which were nearby, so I just drew it and just labeled it once rather than labeling it twice. But even that will do it. Okay? Now you need to connect all of these. So can you do a quick layout? Everybody's done layouts before. You ever done a layout? As part of your course? So, you say what's 3 transistors here. So it says, so outputs, same outputs, plot to be plotted, you have to plot those outputs, right? And select what's design, so select N1. And if you also select N1, so you want to see what's happening in the diodes. Okay, give some value to the footer, some random value to start with. What people will do, it's just a DC value from where it starts. Okay? Now what kind of simulation do you want to do? Select what kind of simulation you want. DC simulation good? What do you want to see? Select the display. And this will give you the option to select. Good. Take some range. Yes, we are lucky. So we can see what is there. On the x-axis is a log scale. Right? Log scale we have already named up, which means my output is logarithmic related to the input. Okay? So pixel works. So that is the schematic side of pixel. So we have got a log pixel which is doing a wide dynamic range response. The next task, of course, is that is not the pixel. The layout will be there. Find a pixel. Tells you step-by-step sequence if you can access it. Okay. If you have time, you're looking for 30 here. Select DC. You want to sweep? Design variable. Select. Always do this because that way you know if the circuit is working or not. Now you need to give some range. Where do you want to start from? No. Never. So the reason why never, we're doing a logarithmic simulation. Where is 0? Is 1 after 0? Is 10 to the power minus 25 0? 10 to the power minus 60 0? 10 to the power minus 90 0? So it's a good idea to give a finite value. So let's give it 1 femto or 1 pico as finite small value. Give 1 pico. And then the largest value, make it about 6 times bigger than that. 10 to the power 6 times bigger, what will be? 10 to the power 6 times, a billion times more than that. So pico, 1000 times is nano. After nano comes 1 micro, 1 U. Okay? Now let's run. Actually, we also want to see what outputs do you want to see. Check the circuit. Just hope you have done everything properly. Let's run. The green button will do. Yeah, let's see what happens. Ooh, works in the first run. Now, what are we getting? What's on the x-axis? It's 10 times, right? So it's on logarithmic scale. And on the logarithmic scale, I'm getting kind of a straight line because they are bending here, they are bending here. The straight line on log scale means this is log of this. Make sense? So x-axis is log, is 10 times. Y-axis is straight line. So what's the relationship between this and this? So if this was 1, 2, 3, 4, we would have said y is equal to mx plus c. Right? But my x is log, or x is exponent is 10 times increasing. So if you get a straight line when x-axis is y, y is logarithm of x. So it's rooted in log of x. Okay? Okay? Good. So the pixel works. At least it gives a logarithmic response. Everyone has got a log response? So what I will do now, rather than showing, I will just show you one trick on to do layout, okay? And then we will go on. So most tools will provide you automatic way to do layouts. Okay, this also provides. We just don't like the automatic way of doing it because we want to put things as compact as possible. So what I will then do is think what is needed to make my transistors. Diffusion section. What's the difference between, so mine is bare naked diode. It is just a bare naked diffusion. I haven't even told it's a n-type diffusion yet. On top of the foundry diode, I have got metal 1 is covering the whole of foundry diode. So it's not a very good diode for me. It's shielding light. And this is why I can't really use the foundry diode. What I could do is take the foundry diode and remove the metal. Or I could just go and straight draw my own connection. So I have now got 3 transistors. and all the transistors end in metal, right? So I can just draw a metal layer as like the wires which I have, and my pixel is done. It's just a bad pixel because it's got loads of empty area in it. Okay? So what I could do is I could start saying, okay, one transistor shares things, right? That could be my source follower and reset switch. And what I know is that kinda gives me my pixel. I've got a diode. From there, I'm connecting to one end of a transistor. Oh, I've done a mistake. And from that end, I go to the gate of next transistor. This is my source follower. The other end will get connected to VDD. This will also get connected to VDD. And then that will get connected to source follower. As you can immediately see, I've done something. I have fused the one end of the two transistors. Actually, I don't even need this. I can get completely rid of this. There's nothing being connected. So between your source follower and switch, that terminal is not connected to anything. Okay. Similarly, I can turn this thing whole around and connect this and that together because they are VDD. Isn't it? So let's do that just for fun. I have a pixel for all practical purposes. It's not a good pixel because you can see a lot of space is left here. Right? I should be able to put these things together and draw the wires as close as possible. But as a pixel, yes, all the circuits, all the transistors are there. That will be connected to the source follower, which is a line which will be running in parallel. So we could say, okay, let's take a metal 2 line. line. One, two, metal. Stack. Most probably it will fail DRC, but for all practical purposes, now you see two lines running that way. The top line is carrying my VDD, the middle line is carrying my row select, and there is a metal 3 line which is coming top to bottom, which is carrying my output. I had to run it through metal 3 because, or else if I ran it through metal 2, these two will short here. And I had to run these two metal 2 because inside the pixel I'm using metal 1. So metal 1 is the lowermost layer which should be good to use inside pixel, metal 2 that side, metal 3 on this side. Now this is another difference between image sensor processors and your classical processor or memory technology. Now in processor technology we have large number of metal stack because you need to run many wires here and there. Now think of it this way, my diode is sitting on the floor, and if I have big stack of metal, then light could go in the sideways before it hits the diode. So for optical processes we want less number of metal, so that from the ground, from the diffusion, there's only a small stack of metal so that light falls straight onto my diode. So here we have designed the whole pixel with 3 metal. Okay? We will do something else as well. I haven't provided ground. Okay? So I need to get a ground. So maybe I'll use the 4th and 5th metal, not only to provide ground, but also to shield all of that area. Light should only fall here. It should not fall on any one of that. So I'll just here. Oh, this is just a connotation. We have in this technology they are using red for diffusion. Some other is just so all these colors denote individual masks. So when the foundry gets this layout, they separate these color, and for each color they know this is one layer of technology we have to make. So here the diffusion is denoted by red color. There are processes in which diffusion is denoted by green color. You can change the color connotation. This is just a way to tell to the foundry this is different than that. Right? At the end of the day, they will take a color map wherein you will say my red means diffusion, my green means metal 3, my blue means this. Right? And they will just separate each one of these layers separately and say, okay, this is where I need to put metal, this is where I need to put my diffusion. Okay? So once we have done this, now you can see why I drew these long lines. Okay? So let's take this is my pixel. I want to create an array. Hypothetically assume this is my best pixel which I have drawn. Now let's make an array out of it. Okay, actually I have an array. So remember I designed one pixel. What did I call it? Log pixel. In the same fashion I designed, let's just do a 10 by 10 array because then it starts becoming. Delta y is okay. Delta x should be about 5.9. So because I drew my lines properly, I can see these lines sorted here and they formed a continuous VDD and row select. And this line forms the continuous row output of this thing. And I have got my array done. Had I spent more time in pixel, the array time did not take me much long, right? And that's a 10 by 10 pixel array for me. Am I at a 200 by 100? I do a 200 by 200 array. Of course, there's few more things required here. I need an ADC here because each line is now carrying, and I need a scanner, a shift register to go from pixel to pixel. But other than that, that's as good as a camera as it gets. Good. We all go home now. What's the time? It's already 5 o'clock. I think we have to stop now. Okay. We'll see tomorrow. We are running a bit behind the schedule when it comes to sensor characteristics. We will take it up tomorrow. Okay. Any questions? Good. No questions. Thank you.